So we're going to continue to do a couple more problems in section 6.2. These are really, really hard, so don't beat yourself up if you're having trouble with them. They're pretty hard. Feel free to use some of the sort of graphing technology that's out there to get a good sense of what it's asking you and how to do it. But be prepared to write it all out and show it out in its to its bitter little details when the test comes around. So there was a suggestion to do number 11. So we have y equals to x squared. That's a standard classic parabola, right? And then we have x equals to y squared. That's going to be kind of like a parabola on its side. If we solve for y, we end up with plus or minus square root of x. So we get like square root of x and then minus square root of x. So that should be easy to visualize, at least that part of it. And then if we go to, let's go to Desmos. Graphing calculator. So we have y equals to x to the second power, nice standard parabola. And then we have x equals to y to the second power. So that's going to be like this. So we're looking at this intersection right there where they cross. So we should be able to do some work to confirm that they intersect at both of these two places, at 0, 0 and at 1, 1. And then it also says to rotate about the line y equals to 1. So y equals to 1, y equals 1 is going to be this line here. So too many colors running around. Let's see, what do we do? Let's make it black, I guess. Maybe that'll work. Okay, so we're talking about rotating this little, I don't know what kind of shape that is, but this little football shaped thing right in here that is in between the blue and the red, and we're going to rotate it in sort of three-dimensional space around this black line, and we're going to get something that almost looks like, I don't know, like a vase almost, right? It's got a curvature on the outside, except it's got a hole in the center, right? And it's got a, it's curved on the inside as well. So it's kind of hard to visualize that. So let's see if this app that I found would work. Ooh, but it's not going to do that. Okay, so this blue one, Desmos does a great job with just being able to graph something that is not in function notation. I don't know that other programs out there do a good job. So instead of doing this x equals to y squared, I can take the square root of both sides, and I end up with y equals to root. How do you do root? Square root of x, like that. See, that takes care of the top half, positive root x. But then I also have to take care of the bottom half, y equals to negative root x. Like that. And now this portion and this portion make up the blue one, right? I can turn that off, turn that off. So this blue function here, let me turn off the other ones just to focus on it. There. That blue one is x equals to y squared. Make this a little bit bigger. So x equals to y squared is this one, sort of a parabola on its side. If I solve it for y, square root of both sides, I get plus or minus root x. So here they are, plus or minus root x. The positive gives you the top half, so that's that purple. And then the minus root x gives you the bottom. So this gives you a way to be able to do this graph in function notation, right? Because individually this black one is a function, individually this purple one is a function, but then this one is not a valid function, right? Okay, now we're interested in the intersection of the parabola, the red one, and the blue one, so really this bottom one doesn't really do anything for us, so I could just ignore that and just focus on that. Good, so it's just root x, it's this purple one, and then this red one. And we want to take the space in between those two functions, this little space right here, and we want to rotate it about the line y equals to 1. Good. Okay, so taking that, let me see if hopefully this other program will work. This one should help us visualize some stuff, so let's see if it'll continue to cooperate. It was working before. Let's get rid of that. And we had I'm going to do root on here. X to the power of 0.5. Hopefully that works. And okay, cool. And the line root x, and then x to the power of 2. Cool. Okay. And we're interested. Oh, shoot. This isn't going to let me do it about a different line. Damn it. And already we fail. Okay, well I can get the general shape. Well, you know, the general shape's going to look like a bowl, kind of like this thing here. But it's just going to be located in a different spot that I can't do with this program. So 0 to 1. Oh, no, it does let me do it. Right here. Is that going to let me do it? Yes, cool. Okay, so here's the line y equals to 1. We have f of x equals to square root of x, and g of x equals to root x. Okay, so here they are. Okay, and then once I rotate this, so let's see. I don't see why. Oh. Come on. There we go. That look a little bit better. Okay, so the green. Oh, you know what? Let's see if I can. It looks better once I do that. So notice that the green is the y-axis and the red is the x-axis. So if I rotate it like this, come on. It's really hard to control this. Whoa, there we go. If I rotate it kind of like this and have the come on, rotate. It's hard to control it. Anyway, you can kind of see in there this leaf shape thing, right, which is a cross section of my bowl. That's this kind of thing, right? So this is this guy right here. And if I move this all the way across, we can see that this little yellow line is this little yellow line. So this is a kind of a three-dimensional sort of looking bowl looking thing, and if I cut it, its cross section looks like this leaf. Okay, so from the outside it just looks like a bowl, but then it's got this hole in the center, right? It's kind of hollow in here. I hope you can see that. It's hollow inside there. And the thickness of it, if I cut it, the shape of the actual material making up this bowl has this sort of tear shape there. And then this little yellow line right there is that little yellow line right there. We're going to take that little tear shape thing and rotate it about this line, y equals to 1. And when you do that, you end up getting this guy. So as it rotates, see it kind of goes all the way around, and you end up getting that. Okay, so if I came through and I cut it, that's what we're going to do with this method, right? We're going to come through and cut my bowl this way, perpendicular to either we have to make a choice. Do we want to cut it perpendicular to the x-axis? Do we want to cut it perpendicular to the y-axis? And so hopefully at this point it's clear that in this sort of question, in this shape, we want to cut it perpendicular to the x-axis. If we do that, see, remember the x-axis is red here. So notice that if I cut it perpendicular to it, I end up getting these washers, right? This yellow, that's one little washer somewhere in the middle. It's got a little thickness. The thickness will be based on the delta x. How thick do I want it? We're going to start off with a nice big thick dx, and then of course we want to set it up in a way where we're going to let the thickness get smaller and smaller and thinner and thinner and thinner, and as we let that thickness go to zero, infinitely small, then that whole thing will approximate the volume of the entire bowl. Right? Now when I say it gets thinner and thinner, that also means that I get more and more washers, right? Because right now, we might start off with, I think at this point there are 42 of them in this little, doesn't do a really great job, but let's see, if we go down to 1, that's just one ring approximating it, that's silly. But if we do, say, come on, there, it's doing 9. Right now it's doing 9 rings approximated, so the thicknesses would be really, really thick at this point to approximate the shape of my bowl, right? And doesn't do a very good, it's not going to do a very good job of approximating the actual volume of that bowl. But then as we increase this, make it higher and higher and higher and higher, then automatically the thicknesses of each individual washer are going to get thinner and thinner and thinner and thinner. And then as we add them all up, that sum is going to become closer and closer to the volume, the actual volume of that shape. And then at infinity, if it exists, if the integral exists, then we'll be able to get an exact volume for that shape. Good. So this sort of behaved itself. I think we kind of have a good sense of what it looks like. Good, 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 good. Okay, so this is called the washer method. And what we're going to do is we're going to visually, kind of draw this and visualize what it's going to look like. So it looks a little like this. And then when we cut it, we got to think about 2 different volumes. We're going to think about pretending it was a solid shape, so there's no hole in our yellow one. So one solid coin. Remember that the formula we're working with is just to find the area of a circle for the yellow one, and then multiply it by its thickness, which is the dx, and that'll give us the volume of the coin as if it was a solid coin. And because it's not solid, as we can see there's a hole in the center, then we're going to find the empty coin, right? The center, the empty space that would have been a coin, the part we would cut out to make it a washer. So think about that, and what's the radius of that empty coin and the thickness of that empty coin. If we subtract them, then we get the volume of the yellow, that washer yellow that's right there. Does that game plan make sense so far? Kind of. Okay, so now that we have a sense of what's happening, let's see if I can write some stuff down. So this is chapter 6, section 2, exercise number 11. And we had y equals to x squared, comma, x equals to y squared. And we want to rotate about the line y equals to 1. Okay, so guided by some of the cool technology, then we can do a nice little sketch. So that's the y-axis, that's the x-axis. We know that we had a parabola that went this way, and we had another one that went this way. like that. So this one is y equals to root x. And I know that there's another one down here, but we don't really care for it, right? Because all that really matters is, you know, let's stick to the yellow that I had in my thing, is this. This yellow part here is all that matters because it's where it crosses. So I care about this guy right there. I care about this guy right there. That's where they cross. That's where they intersect. It's the area in between these two curves. And I don't really care about the rest. The parabola also kind of extends this way, but at this point it's just going to be messy. And this one has another portion down here, but at this point it's just going to be messy. Good. Okay, so now technically we need to find these 2 points, even though they should be pretty obvious, and even though technology has already kind of helped us, we need to show how we would have found that. So we have x squared. Well, I like to do this step myself. Wait. Whoa, cool. That's a little too hard, too big, medium. Okay. So I like to do this step myself, although it's a little redundant, but I feel like it helps. I have the A and I have a B. So there's some ordered pair A, comma, B that I'm trying to find, right? The place where they cross. So at the point A, comma, B, it's an ordered pair that's on the green line. It's an ordered pair that's also on the blue line. So it satisfies both equations, right? And just to make sure it's clear, this equation here is y equals to x squared. Okay, so it must be true at that point where they cross. It must be true that whenever you take the so that b equals to a squared, right? The a squared must be equal to the b. And also at the same time, at that point, it's on the green one, so it must also be true that b also equals to the square root of a. Good. Okay, so now we need to solve for these guys. So if we, well, they're both equal to b, so it must be true that root a equals to a squared. Good, good, good. Well, we could square both sides. Square this side, square this side, and we end up with a squared squared root a squared. So this gives me a equals to a to the 4th power. Okay, so move it over. So we get 0 equals to a to the 4th power minus a. And then we factor out an a, and we get that a is a cubed minus 1. Okay. And so from here, we have the zero product principle. So that must mean that a equals to 0 is one solution. And we also get that a cubed minus 1 equals another solution. So a cubed equals to 1. And so that must mean that a equals to 1. Good. So it's really the cube root of 1. Should have done that. It's the cube root of 1, which means a equals to 1 is the other solution. A equals to 1 is the other solution. And now we can go back to our other descriptions. So say, for example, from here, we can get that b equals to a squared. So b equals to 0 squared is one answer. So b equals to 0. That's how we get the point 0, comma 0 as one solution. And then going back to this other one, same formula. Now going back over here, we get that b equals to a squared, and a was a 1, so b equals to 1 squared, which means b equals to 1, and that's how we get the other ordered pair using using these two. we get that 1, comma 1 must be that other ordered pair. Right, so all that work just to show that these two are the intersect points of these two functions. So now I can go back over here and get rid of my a comma b. I don't need it anymore. Or I can just point to it and say that that must mean that this is 1, comma 1, and that this, just as we thought, was 0, comma 0. Good, 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 good. Okay, and then of course we're going to have the line y equals to 0, I'm sorry, y equals to 1 kind of go right across here. So we're going to have the line like that of y equals to 1, and we're going to rotate this yellow thing around that. And this is where my terrible drawing skills come in. Let's see. It's going to be this shape this way, and then it's going to have a kind of a shape like that, and then it's going to rotate like this, I guess. Something like that, I guess. Really ugly. Good thing we had that technology to help us visualize it a little bit, because this thing's pretty ugly. Any rate, hopefully it's passable. Okay, so we're going to have a coin, right? We're going to cut right through this thing, and we're going to have a coin that cuts through the center of this thing. So it's going to have a certain thickness to it, and it's going to go across this way and this way, and it's going to have a little thickness to it, like this, except it's a hollow coin, a washer, so it doesn't go all the way through. There's going to be a little thing there. Okay, sort of, kind of, sort of, kind of. Okay, so in order to figure out the volume of this coin that I have going on here, I'm going to first of all pretend it's a solid coin. And if it's a solid coin, then you know, this coin here coming back to here is going to be a coin that kind of comes here and looks like this. Right? This is the cross-sectional area of my coin, kind of rotating about its center, and it's going to go from its center, which is y equals to 1, all the way out to the bottom, which is going to be the y equals to x squared, right? The blue one. Good. So from the center to the outside one, from there to there, that distance is going to be the radius that goes out from the center of the coin all the way out to the outer edge of the coin. Good. From there all the way out to there. Oh, that's okay. Let's put it in a different color, not blue. From there out to there, that is going to be the outside radius, right? It's good. If there was no other, if the green coin wasn't there, I was just rotating that, I would get like a solid bowl, and then when I cut it, I would get solid coins. So that distance right there is going to be 1 minus the y value, right? The height, the y value of blue line. Does that make sense? Any questions? The blue line, let me highlight, that's this one, right? As I slice across, it's always going to be 1 minus the y value of the blue line. 1 minus the y value of the blue line. Good. And the blue line is determined by this. So the y value of the blue line is determined by x squared. So it'll be 1 minus x squared. Is that okay? That'll be this radius from there to there. And then the little one going from the center out to the edge of my washer, in other words, the radius of the empty space, it's getting kind of messy, I hope you can see what that is going to be the same as the distance between the 1 and the little gap that's right there until it touches the green one. Good. So it'll be kind of like from there to there. This little space right there, that'll be the radius of this empty coin in the center, the hole we're going to take out from our coin. And that distance right there is going to be 1 minus the y value of this green line. Good. So this little distance right there is going to be 1 minus the y value of green line, green curve. Good. Good, 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 good. So if I was just going to find out the volume of a solid coin of this red one, pretending there's no hole in the middle, the volume of that solid coin would be equal to pi r squared. It would be pi times radius squared. And in this case, this is my radius. 1 minus x squared is my radius. So it would be pi 1 minus x squared squared. Good? Questions, 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 questions? Right? So this gives me the volume of this red coin if it was a solid coin with no hole in the middle. Now if I think about that hole in the middle, if we think about the coin, the volume of the empty space, an empty coin, the radius is going to be equal to 1 minus the y value of a point on that green curvature, which is root x. Root x. Good? Good, 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 good. Okay, so then the volume of that empty coin in the center is going to be pi and then radius squared. So it's going to be pi times 1 minus root x squared. Good? Okay, so this is the volume of the empty hole in the center. This is the volume of the solid coin if there was no hole. So if we subtract this one minus that one, we'll get the volume of the actual washer, right? So we're interested in this washer here. It's like a coin with a hole in the center. And so if we subtract this one minus that one, we'll get that one. Okay. So one single coin is going to be the difference between those two when we choose a specific value of our x. If we choose one specific value of x and we punch it in, we'll get this. Sometimes we denote that by saying it's like a little star value, right? Putting like a little star to indicate that the x is some specific chosen value of x in the region we're interested in. And we might do several of these. Remember, if we're going to do n of them, we might say we subscript them with an I. So if we want an approximation, we want to add up several of these. So maybe do 10 of them, right? Cut it up into 10 equal portions and add them up so that becomes a good approximation. So now if we bring them together, we would say that a good approximation would be a Riemann sum. A Riemann sum of i's as they go from 1 to, let's make it 50. We're going to cut it into 50 washers, right? And then the volume of each washer is going to be equal to pi 1 minus x sub I star squared. and the whole thing squared. That gives you the volume of the coin minus the whole, which is going to be pi 1 minus root x star sub I, the whole thing squared. That times delta x would give you a very good approximation, right? This is saying we cut up our space between 0 and 1 into 50 equal little pieces. From each individual little slice, we're going to pick x sub 1 star, x sub 2 star, x sub 3 star, right? Let me zoom into there and see if I can push that in there. Right, so we're going to cut this up into 50 equal spaces, 50 equal spaces. From each individual little space, we're going to pick x sub 1 star, and then the next one is going to be x sub 2 star, and then the next one is going to be some randomly chosen value, which is going to be x sub 3 star, and so on and so forth. So eventually the last little spot is going to be x sub 50 star, right? Okay, so we have 50 coins, and if we find a good approximation for the volume would be to find the volume of those 50 coins, add them together. That gives you a pretty good approximation. So that's what this is. Any questions about this guy right now? Okay, well, just kind of extending that. Instead of saying 50, we can erase this, if it'll let me erase it. Erase this and say, well, don't just do 50, do it for n of to be a good approximation as long as we let n be large. The bigger it is, the better the approximation. Good. And then the calculus comes in where we apply the limit as n goes to infinity of this whole thing. Actually, I'll just write it right here. We could just say, okay, well now let's apply the limit as n goes to infinity of this whole thing, and then it's no longer a good approximation, it's just the volume. It's no longer an approximation, it's the volume, if it exists. If we have a problem with it and we can't find it or something, well, that's another story, but assuming this whole thing exists, everything's fine, then we got ourselves the volume. Good. All right, well, all of this is, by definition, an integral. Right? So the volume is going to be equal to the integral of pi 1 minus x squared, whole thing squared, minus pi 1 minus root x, whole thing squared, the whole thing multiplied by dx, and x ranges from 0 to 1. And again, personally, I like to clearly identify the variables of integration there, just so there's no mistakes, no miscalculations. Good. Any questions at all? Okay, so this is what we're tasked with figuring out, the integral of this thing. If I can figure out this integral, I'll get the volume of that shape. A couple things right away to make things life a little easier. I can factor these guys out. It's just a constant, it's just a pi. I can distribute, oh wait a minute, I have to square first. So I can square it and then distribute this minus across. I can square this thing and then distribute the, or combine like terms. So let's go ahead and do that. Factoring out the pi, okay, when I FOIL this guy out, let me put it in blue. When I FOIL out this guy, I'm going to get 1 minus twice x squared plus x to the 4th. That's just foiling this guy. When I FOIL this guy out, I'll get 1 minus 2 square root of x plus x. Right? That's just this guy. And then when I when I distribute this minus across these two, I'll get 1, I'll just put it down here. I'll get pi there on the outside, factoring it out. And then I'll get an integral as x goes from 0, x goes to 1. And I'll get a 1 minus 2x squared plus x to the 4th minus 1 plus 2 root x minus x. Right, as I distribute this minus across these terms. And then these two terms cancel, so that's good. This cancels with that. And nothing else happens. Let's not forget our dx. Good. Okay, well luckily this is just a polynomial, right? In fact, I can also rewrite this as x to the power of 1/2. And then I can just follow my standard rules for polynomials. So let's do one more. Let's rewrite this as pi integral as x goes from 0, x goes to 1. Let's put the x to the 4th first, highest power. The next power is the minus x, minus 2x squared. Minus 2x squared, that takes care of those two, minus x plus 2x to the 1/2 power dx. Good. Okay, so then following our standard antiderivative rules, this is going to be equal to 1/5 x to the 5th minus 2 times 1/3 x to the 3rd plus 2 times, and this is going to be 1 over x to the 3 over 2, x to the 3 over 2. Notice I've been adding 1 every time. Add 1, add 1. So if you add 1, you get to 1/2, which is 3 over 2. And the pattern is always to divide 1 over that factor, so you can write it this way. Or you can also just note that this is 2/3 if you simplify it, right? Whatever makes most sense to you. Good. And all of this gets evaluated as x ranges from 0, x goes to 1. So luckily, lots of stuff will happily simplify here. You get pi, parentheses, 1/5, something to the 5th power, minus 2/3, something to the 3rd power, plus, now this is going to be 2 over 3, which becomes 4/3, 4/3, something to the power of 3 over 2, and all of that becomes the same thing in the other, 1/5, something to the 5th, minus 2/3, something to the 3rd, plus 4/3, something to the 3 over 2. Right, so it's this minus this, where first we plug in the 1s, so 1 goes there, 1 goes there, 1 goes there, minus, and now we plug in 0s everywhere. So 0 there, 0 there, 0 there. Luckily, the 0s make life super easy. 0 to the 5th is 0, 0 to the 3rd is 0, square root of 0 is 0, the whole thing is just 0, this whole thing is just going to become one big 0, minus 0. So it doesn't affect anything. And 1 is super easy as well. 1 to the 5th, 1 to the 3rd, they're all just going to be 1. Right? So this is just going to simplify to give me pi times, and I'll have 1/5 minus 2/3 plus 4/3. Good. Common denominator of 15. So multiplied by 3 over 3, multiplied by 5 over 5, multiplied by 5 over 5. and we end up with pi, and then this is going to be 3 minus 10 plus 20 divided by 15. So that's going to be 13/15. Something's wrong. 10, 13 over 15. I got something wrong somewhere. That's not the answer here. Why am I missing a term? I'm missing a term and you guys didn't tell me? I blame you guys. Let's pretend I did that on purpose to see if you were checking. Guys, I totally... What happened to that term? I got x to the fourth goes there, and then x to the second, that gives you that. And I completely left this blank. So there's a term that goes in there. It's going to be equal to minus 1/2 x squared. Right? So then that means there's a minus 1/2 x squared. So come on. Could have been blue. Minus 1/2 x squared plus that. So I have to squeeze that in there. And that means I also have to squeeze this in here. So there should be a minus 1/2 something squared plus that. And then, of course, that's going to be a 1 in there. And then there's going to be another term over here, which becomes a minus 1/2 something squared plus that. Luckily, again, it's a 0, so that should make life easy. 0 there, 1 there. Good, 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 good. Okay, so that's still going to be 0. That goes away. And this is going to be minus 1/2 1 squared. So that's just going to be a minus 1/2. So I should end up with an extra term of minus 1/2 in here. Okay, so then let me just redo this part because then I need a common denominator that's a little bit different. So this will end up being pi, bracket, 1/2 minus 2/3. There's a minus 1/2 in there. And then plus 4/3. Okay, so now common denominator is no longer going to be 15 because of the 2, so let's go to 30. So times 10, 10, times 15, 15, times 10, 10, and times 6, 6. That gets me to 30. So let's see, we end up with pi, bracket, I get 6 minus 20 minus 15 plus 40 divided by 30, which gets me to pi times, that's going to be negative 35 plus 40 gets me to positive 5 plus 6 gets me to 11 over 30. Oh, okay, yeah. Now it matches with the, I'm looking at the correct answer, and it matches. So there's our answer. 11 pi, that looks weird. Let's get rid of the bracket. So 11 pi over 30. Any questions? No questions, no questions, no questions. No, no. All right, let's do one more. What are the, let's see what the homework assignments are for this thing. Oh wait, I think it's over here, isn't it? Yeah, I did. Here. Okay, so 1 through 17, 19 through 29, just set it up, plus then 47, 47, 54, 56. So let's look at. All right, so I think we covered a few of these from 1 through 17. That should be fine. And then 19 through 29, it says just to set it up. 19 through 29. Good. Okay, so here they give you a nice little picture. We have the fourth root of x, region 1, region 2. Okay, so they just wanted to answer those. Region 1, about the line OA. Refer to the figure and find the volume generated by rotating the given region about the specified line. Region 1. Okay, so the blue part rotated about the line segment OA, which would be this. So if we rotate it, we would end up with something that looks like a pyramid, like a perfectly, well, a cone, a perfectly pointy cone, right, that comes right up to this little tip, right? It'll have a big base over here as we rotate it this way about the line OA, which is the x-axis. Good, good, good. Okay, so think about how to find an integral that gives you that particular volume. I think those should be fine. So like I said, from like I was noted, from 19 through 29, just set it up. Don't worry about finding the actual integral. Once you set it up, just stop there. Oh, okay. So now these are a little bit different. The base of S is a circular disk of radius r. Parallel cross sections are perpendicular to the base are squares. Okay, so this one's a little bit different than what we've been doing. We're going to think of it as a floor and sort of a roof, and we're going to put rectangles kind of extending out to that roof line. So how do we do these guys? I think there's some nice graphics in the book for this thing. Alright, well, this is one of my terrible drawing skills will come in again. So think of a three-dimensional space, like a grid like this, and there's going to be a circle on the floor that goes out from there and kind of comes across this way. So think of that as a circle on the floor. And what we're going to do is we're going to come across and we're going to draw lines that cut this way on the circle. And so that will become one side of a square that kind of comes up. This kind of comes up and creates a square. It's going to have a little width to it, so it'll be like a box. And then we're going to do that all the way across. So way over here, there's going to be another one. Comes this way. And then again, we're going to have it come up. Oh, I think that that's not quite right. It needs to be more like that. And then it's going to come up. And make a square like that. So we're going to do that throughout the circle. So obviously as we get closer to the edges over here, the line segment is going to be smaller. So the little squares are going to be smaller. And when we get to the center one is going to be the biggest rectangle, right? It's going to be out to there. And it's going to come up and have itself a nice big square. Sort of, kind of, maybe. Okay, so what we're gonna do is take our floor, we're gonna chop it up and come up with approximations by, let's say we begin by just doing what I did, 4. 1, 2, 3, 4 of them. One in the center, one there, so there's 4 of them. It's a rectangle, so it's going to be whatever this distance is right there, the red line on the floor. If we multiply that times 4 of them, right? This times this will give you the area. Not multiply times. If you multiply the side times itself, so side squared, s squared, will give me, let's call it sub 1, side 1, would give me the area of that squared. And then if I look at the next one, I don't know, too many colors here, but if I look at this side of this second one, let's call it s sub 2, if I square it, I'll get the area of this other square. And then same thing for all of these, right? So now if I look at that one, that would be s sub 3 squared. And then this last one, s sub 4 squared. And that'll give me that distance there. Good. And then I just have to multiply it times its little thickness to give me the volume of each individual rectangle. Good. Okay, so now in my image, in my picture here, this is the y-axis, this is the x-axis. So I have to think about how do I find those distances there, right? The circle is controlled by the equation y equals to x squared plus y squared equals to the radius squared, right? That's this equation here for any circle. So if I find an equation for the, well, I guess in the way I've drawn it, I need to find the distance of each individual x, like this, and so this kind of maps down to here to be some x value. Good. And once I find the x value, which is this distance there from the origin to that point, that's the x value, then that means that that side is twice that much. Good. Questions? So the way I've drawn it, it's always going to be side is equal to 2 times the x value. Good. Questions? Okay, well then I can solve it right here. That would be x squared equals to r squared minus y squared. And so x equals to the square root of x squared minus y squared. Now, when I took the square root, you end up with a plus or minus, which reflects the fact that you're going to be graphing graphing that parabola for the positive and the negative end. But if we just stick to quadrant 1 and make everything nice and happy, in quadrant 1, then we only have to worry about the positives. And so if we just figure out what's happening in this, in this half of it, we should be able to figure out the whole thing. Good. So the side of each rectangle is going to be equal to twice times, and then this will be equal to square root of r squared minus y squared, which means I'm integrating with respect to y, right? The way I've drawn it, I'm chopping up my space this way. Good. So I'm going to have little thicknesses which are going to be dy's. So I need to multiply it by dy. Good. Questions, 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 questions? So therefore, the volume of the resulting shape, volume, is going to be equal to the integral of, and now I'm integrating with respect to y, so this would be y ranging from, and it's going to go from there to there, so that's going to be y ranging from negative r to positive r of twice times square root of r squared minus y squared. This is the side, and then that whole thing gets squared. This is the area of each rectangle times its little width. Good. So the volume is going to be equal to the integral as y goes from negative r, y goes to positive r, of 4 times r squared minus y squared dy. Everyone with me? And now, now we can take advantage of some symmetry. If I can just figure out the first half, right? I chopped it this way. I have a bunch of rectangles going in this direction. But if I can just find half of it and double it, I'll find the volume of the whole thing, right? It's going to be symmetric that way. So instead of going as y goes from, so this is saying y, here is negative r on the y-axis here, and here is positive over here. This is positive r. Remember, this is the y-axis here. So instead of ranging from y goes from negative r to positive r, we can go from 0 to r and then double it. And the reason why that's nice is because throwing in a 0 usually makes life easy, right? So I would say that my volume is going to be equal to twice the integral as y goes from 0, y goes to r of this thing, 4 times r squared minus y squared dy. Questions, 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 questions? No? Maybe? And that's actually a fairly easy integral to find, right? Remember, r is some constant. It's a radius of a circle for the floor of this shape that we don't know yet. So it's a constant to be described later. I can pull that 4 out, make it 8 out there. So I end up with the volume equals to 8 times the integral of r squared minus y squared dy. And again, y goes from 0 to y goes to r. And simplify that over here then. So this will be 8 equals to r squared y minus 1, wait, why did I say equals? Equals 8 times r squared y minus 1/3 y to the third power is evaluated as y ranges from 0 to y goes to r. And that's my volume. So the volume is going to be equal to 8 times r squared times r minus 1/3 times r cubed minus, and then the other ones are going to disappear anyway, but just to make sure people are following where I'm doing with this, I'll put r squared times something minus 1/3 times something cubed, and all of that gets multiplied by that 8. And so we had r there, and 0 there, and 0 there. That makes that easy. And so this is going to be r cubed, and we have 1 minus 1/3. All of this is going to end up being 2/3 r cubed times 8 equals my volume. So my volume is going to be equal to 16/3 r cubed. Any questions? Let's see if I can figure out how to use this thing in a nice way. Let me will it do shells, diamonds, semicircles, equilateral sections? There's actually square sections. Rectangular sections, square sections. Does it do that? Oh, okay. This is going to do what I think it's going to do. Okay, cool. And we had a circle. What's going to happen here? This is going to be equal to it's not going to like the R. One minus x to the second power to the power of 0.5 okay, so I'd like that circle. You should still be able to get a pretty decent picture out of it, even though we don't have, it's not going to like the R. So this should be the same thing, 1 minus x to the second power what? Parentheses 1 minus x to the second power, close parentheses, to the power of 0.5, and then we want, oh, it does not like that. I want -1 times, and then we have 1 minus x to the second power to the 0.5. Yes, okay, so we got ourselves a nice pretty circle, and we're doing rectangles on it, and we want to go from -1 to +1. So this isn't going to be a perfect implementation, but it does a really good job. There we go, that looks better than my own picture. Okay, so do you see how we get this circle on the floor? This is like looking at this building from the ground up. And then once you've built it, it looks like this. It's a bunch of rectangles. One rectangle, another rectangle, another rectangle, another rectangle. Right? So here is the yellow one is that rectangle that goes across the bottom of the floor. That's this one. So as that rectangle changes, toward the tips we have very little rectangles, like that one. Much smaller little rectangle. We need to figure out that distance right there, that side, and square it, and then we'll get the area of a rectangle. And then if we multiply it times its thickness, we'll get the volume of that little rectangle, right? And as we change, go toward the center, we get bigger and bigger and bigger rectangles. Like way over there, we get a much bigger rectangle. We get the biggest rectangle right there at the center. That's when we'll have the absolute biggest rectangle. Kind of hard to see, but it's right in the middle there. I think if we take down the end values, we'll see it better. There we go. There's that yellow rectangle there. Why isn't it centered, I wonder? Okay. Good. Okay, so you know, as we rotate across, we get different rectangles. We have to come up with this equation from the center to the outer edge. Now, this particular programming here, I don't think it's going to like it if I put a variable r to represent the radius. I can look, but I mean, it's probably not going to do a very good job. I can change it to something else, like you know, the radius is 1, or maybe the radius is 4. Let's change it to a 4 here and see what happens. So you see, nothing really happens. It's just going to be a bigger circle, so it's like a bigger building, but the shape stays the same. Oh, I just have to make sure that I go from here I limited it from -1 to 1 because I was doing a radius of 1, but now I'm doing a radius of 4. So from -4 to +4. Will get me the whole thing. Good. So we still see it as it rotates. Any questions? Questions? Anybody? No? Are there any other recommendations for something to do from 6.2? Anybody stuck on anything? All right, so keep working on that homework and let me know if you get stuck on anything. In the meantime, we're going to move on to 6.3 then. All right, section 6.3, volumes by cylindrical shells. So we're still finding the volume of certain shapes, except we're going to apply a different method, a different technique, a different way of looking at the same thing. And in some cases, one method is better than another. So here, consider this example. Let's say we had, let me zoom in here. Whoa. Let's consider the problem of finding the volume of this solid obtained by rotating this function about the y-axis. So we rotate it this way. Can you kind of visualize what that would look like? Right? If we rotate it about the y-axis, to me this would look like a mold to like a bun cake. That's what it would look like to me. Well, actually, the bun cake itself is probably what it would look like to me. Is there a nice picture of it somewhere down here? I get like this one, right? So that's sort of what it would look like. Is that the sort of, except it's going to have a flat base over here, and no way that I can draw that. Let me see. It's going to have a sort of a flat base, and then from the center it'll roll out to some sort of a kind of a thing like this. And that's ugly. Like that, but then it'll kind of rotate. Wow, that's really ugly. And it'll rotate. Oops. Oops. Wow, that's really ugly. Anyway, okay, so it's kind of like a bun cake, if you know what a bun cake looks like. It's not really, this is not very good at all. So, kind of like that, I guess. So there's like a hole in the center here. Something like that. Okay, so if you think of a bun cake like this, and then we go forward with our coin method, we would have a bit of a problem, right? If we cut it in this direction, if you think of a bun cake, I wonder if I can just look up a picture of a bun cake. Just bun cake? Bunt cake. Bunt cake. Bun cake. Image. Yeah, looks kind of like this. Right, this is like a nice, perfect one. As an image of what this sort of looks like. So ours is going to look sort of like this, except that it comes to a dot in the center, right? So it's going to be, actually, there's not going to be a complete hole there. It just kind of curves and goes toward the center. Oops. Getting into recipes or something here. Oh, okay. Anyway, so it's going to come out and curve into the center, right? As I slice it, we'll see that shape of that curvature. What is happening here? Close, go away. As we slice it, we'll see that curvature come into here that we have, but ours comes down to a center at the origin, so there won't be an actual hole through it, but it would be an empty space like this here. Good, sort of. Maybe that kind of helps visualize this cake thing here. Okay, so then the problem is, though, with our technique that we've been doing, is that if we cut it in this direction, if we come through and slice things, is it clear that if I slice it this way, I'm not going to get a coin? If I slice it this way, I'm going to get kind of weird shapes, right? If we go back to this image over here, if I cut it this way, I'm not going to get coins. I'm going to get weird ovular shapes, right? And they're all going to be different up until I get to the middle part, and then it gets even weirder because then I'll get some cake over here and some cake over there. It'll be like a weird empty thing in the middle. So slicing it in this direction is no good, right? Okay, now we can slice it this way, going along this way. And if you think about slicing it along this way, we would get a washer. Right, so let's get rid of this thing. So if we cut it along this direction, we would get a washer, kind of like that. and it would be like a little empty hole in the center, and we would get a little thickness, and I'm making it extra thick, but it doesn't quite have to be that thick. Kind of like that. And here's my thickness, and then here is my center. Okay, so it looks promising. Right here is the face of my coin, my washer, is that. The problem though is that in order for me to figure it out, remember I got to figure out the distance between here to there, and then also the distance from here to there to figure out that emptiness. Is that okay? That makes sense? In order to figure out my radius, I need the radius is going to be the solid coin. I need to go from, let's see if I can make it bigger, from there all the way out to there. I need to figure out that distance. That's the outer radius. Radius of the outer, right? And then I'm going to subtract off this part here, which is the inner radius. Let's put it in purple. From there to there, I need to figure out this radius of the inner part. Good. So in theory, it sounds good, no problem. Oh, you know what? I should have stuck to the right and the left, like the way they have it here. But at any rate, the problem is that the exact same equation describes this outer edge of my shape. So when I give an input, I choose one particular value of y. So like say when y equals to 0.73, just a randomly selected number between 0 and 1. Let's say I pick that value. Then I got to figure out which is the x value that belongs there and which is the x value that belongs there. There'll be two of them. There's an x left and an x right. Ugly. Very ugly. And I got to do that for each individual slice that I do. I always have to figure out, well, which one is the one that's the smallest value, that's the inside one, and which one's the biggest value. Now, if I was doing it for 10 coins, I can manually do it, no problem. I can just figure it out and do it purposefully. But if I'm setting up a system where there's going to be an infinite number of coins, how do I figure out which one is always the smallest one so that I can use it for the inner coin, and which one's always the bigger one for the outer coin? So it gets complicated. Good. So clearly we need a new way to do this, a new perspective on the same question. Is that clear? Is it clear why we have a problem doing it this way? Yes? If I can come up with some great equation, right, if we want to like stick to this, if we're really stubborn and we want to stick to this, one thing we could do is come up with a unique equation that describes this part. That way I know that the lower part is going to be described by the point that's on the green part of it, and then come up with some other equation that describes exactly this part of it. That way I know that the XR is always the point on the red one. Good. So if we could do that, then we could continue to do it in the way we've always been doing it. But that's work. That's ugly. Good. And leaving it as just one simple equation like this one, this equation describes all of it. It describes the entire thing. It's just that for some values of x, it's going to give us, for some, there's going to be a value of x. There's going to be two values of x. One's lower, one's higher. Okay, so we're good on the problem. We know that that's why we have an issue. We can't do it the way we did it in the previous section. We're going to have to do it in a new way. And that new way is cylindrical shells. What we're going to do is we're going to come up from on top of our cake. Instead of slicing it across this way, we're going to come up with a knife from up here and cut around it so that we end up with a like a sliver that goes all the way around. Think of it like onions. The little shells of the onions. We're going to peel out onions, and those onions are going to give us cylindrical shells for this thing. I know it's kind of hard to imagine at first. But one shell is going to look like this. So let me see if I can... I don't think it's going to let me do backspace to that. So let me go back to this thing over here. No, it's not going to do it. I have to do it again. Wish me luck trying to draw that again. Alright, so we had some sort of a circular base, and we had this thing that kind of... Not that the base is too big. Whoa, that did not like that. Okay.
Does that software allow you to just copy the existing line work over to the side?
It probably does. I just don't know how to do it. I know. I'm getting old. I don't know things. Sure, there's a way to select it and copy it, but I haven't figured out how to let me select it. Does anybody know on OneNote how to do that? You can do a text. See, I would think it's this thing, but it won't let me do it. If I do this thing, I think it would let me copy it.
Copy. You just do Control C, Control V.
Yep. Oh. It didn't work before. How come it work now? Awesome. Thank you. Yes. Oh, that looks stupid. Oh. Oh, exciting. Okay. Sort of. Cool. Alright, so let me just erase some of this thing then. So I need to erase that over there. And let's make this small. Erase that. And erase that. And erase that. And so we're not going to come across this way. I'm going to end up erasing most of it anyway, so it's still nice to have the shell of it there since I'm a terrible drawer. Okay, so back to this guy. Alright, so let's fill in this guy. It came this way, and this guy came in this way, and then kind of came up that way, came up that way, and there's this back thing back there, and then okay, so sort of like that. Okay, so instead of slicing it across this way, you're going to take your knife, and it's going to come back from on top of here. So here's your knife coming this way at it like this, and you're going to cut into it, and you're going to make a little incision, and it goes in here, and it's going to go like this down to there. You're going to slice it like that, and then you're going to go all the way around very carefully, going around your cake. And then once you make like a little cut incision all the way across, then you're going to make another little incision right around it, like this. So you'll end up with something, well, you'll end up with something that looks like this guy. Okay, sort of, kind of, maybe. So a bunch of these little shells are going to make up the shape. When I slice, when my knife comes out near the edges, we're going to get a shell that's really short, not very tall at all, right? When it's close to the edges, we're going to get a shell that's very short, but very long, very wide. It's going to be kind of like this, very big like this, and then comes across, and then it's very thin. Oops. Like this. Right? So that's on the outside. And then when you go maybe a little closer to the center, then we'll have another sort of thicker one. I mean, sorry, taller one. Maybe that's a little too tall. And there's another one that's like a little bit taller. Still has that same sort of thing over here. Comes up to here. Kind of like that. So it'll be this other shell that's right on the inside of it. And then you go a little bit farther in, and then you'll get another shell, right? So you end up with all these shells that kind of stack up inside each other. Okay, they're getting really messy here. They stack up inside each other, and together they begin to give you this sort of shape. When there's only 4 or 5 of them, it's not going to look very good. But if we end up doing thousands of these things, then eventually they do a pretty good job of approximating it. Good. Sort of questions, questions, questions. Okay, enough with my hand-drawns. Let's see if we can get technology on the case. All right, so that's the Bunsen. Let's go back to this guy. Okay, so here we have our equation. 2x squared minus x cubed and y equals to 0. So here's this shape right here, and we're going to rotate it. So let's increase this guy up. So there's what it looks like, a little Bunsen guy like this. Let me zoom out a little bit. Okay, so we have, come on, not rotating how I want it to rotate, come on. There we go. Whatever, okay, there. I don't know why it's, stop. There, okay, whatever. It looks like this. And the shells are going to be these rings. So I'm gonna bring this down a little bit so that it's a little easier to see the individual rings. So let's say I have this guy right there. Come on. It's just gonna fight me. Come on. No, okay. There's the graph, and then it gets rotated, so it gives us that shape. Okay, going back to this. Now if I just have one ring, then that ring is going to go around and do that. Trying to see if I can get a shot. No, rotate the other way. Ah. This thing is so annoying. Okay, whatever. Okay, so it's kind of hard to see, but see how that thin little guy is right in the middle there? But then as I move it, it's going to go toward the center. It's going to be a tiny little guy, and then as it goes up, it goes and becomes a really bigger one, and then a smaller and smaller and smaller one. Is that okay? Any questions? Any questions? You see the knife kind of coming up from on top here and slicing all the way around? And we'll end up with one of these shell-looking things. Wish I had I don't have much control over this thing. Whatever. Okay. Any questions? 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 No. 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 Oh, okay, that looks better to be able to see how it changes from the innermost part of my Bunsen, it gives me that little yellow guy. And then as I go up, and it gets bigger and bigger and bigger, I kind of hit the max right around there, and then it'll get smaller and smaller and smaller and smaller. Right, so look at the outside one. It's it's not very tall at all, but it's really big. Good. And now this computer program here kind of represents the yellow as having no thickness, but that's a little misleading, right? It's going to have some sort of a thickness to it. That's going to be our dx. Remember, the x-axis is in red, so we're going to chop this up into n equal spaces, and it's that dx that's going to be the width of my shell. The height of the shell is going to be determined by the height of this function, right? From the x-axis all the way up to the height of it. For each input of x, we get one unique value of y, so therefore we don't have that same problem we had before. Good. And then the other important thing is going to be to figure out the circumference of this. And remember that the circumference of a circle is equal to 2 pi r. And for any one of these yellow guys, the circumference, the radius, is going to be determined by a value on the x-axis. So right now where it's sitting, it would go from 0 up to whatever that value is there, and that'll be its radius. And then 2 pi times the radius is equal to the circumference. Of course, I just finished saying that this isn't actually a thin sheet. It's actually like it's got a little thickness to it. So there's going to be two different x values, sort of an outer one and an inner one, or a right one and a left one. So which one do we use for that? Well, we can just approximate it and say it's the one in the middle. So you can just add those two values together and divide by 2. That'll give you the mean one, the mean of the x value, and you can use that as the radius of any individual shell. We'll come back to that as we move forward with this thing. Okay, so any one of the shells looks like this. It has a little thickness to it, right? And then we have sort of the outer radius. That's this r sub 2, the outer radius. And then there's an inner radius out to the center here, which is r sub 1. Depending on how we end up doing it, right? So this is more generic. Specific to this question here, specific to this one, we would end up with a dx is going to be equal to our dr. And so for us, we'll have an outer x value and an inner x value, and sort of the mean between the two will end up being our radius. Good, good, good. So this is called the method of cylindrical shells. Okay, its volume V is calculated by subtracting the volume V1 of the inner cylinder and from the volume of the outer cylinder, right? So, and that's sort of so we're gonna sort of figure out, kind of like with the coins, we figure out the empty space, we figure out the volume of the whole thing. If it was one solid piece, we subtract them, and then that'll give us the actual volume of our little cylindrical shell. The volume of the outside one is going to be equal to pi r squared, right, where the outside radius is r sub 2, so pi r sub 2 squared times the height. This little formula tells you the volume of the entire cylinder if it was solid with no hole in the middle. Good. Now the empty space in the center, well, we just think of a cylinder that's that empty space, and it is r sub 1. Goes from the center out to r sub 1. It's going to be a little bit less than r sub 2. Cylinder in the center. So if we subtract them, the solid cylinder with everything, no hole, minus the empty space, we get to this little equation. And this little equation is now the equation for just the volume of this shell with a thickness delta r, where delta r is the difference between r sub 2 minus r sub 1. Good. Okay, so that tells us this little equation. And then if we factor this guy out, right, this is a difference of squares, so we can factor it out this way. And then we can separate it out this way. Right? All we did was move this h there, and then we introduced this 2 over 2. Right? 2 divided by 2 is 1, so it's just a little trick to introduce that 2 in there. And why would we do that? Well, 1/2 r sub 2 plus r sub 1, this is the mean between the two, sort of the average of the radius of the shells. Right? We just said that. Here's R1, here's R2. If we add them together and divide by 2, we'll get the value of the radius going out to the center of this. It might not be clear from this image. Let me zoom in a little more. This guy, this R, is going right to the center of this. It's right in the center. So R sub 2 is going out to the outer edge. R sub 1 is going to the inside edge. So if we take 1/2 plus, no, not plus. Yeah. If we add r sub 1 plus r sub 2, add them and multiply by 1/2, we'll get that mean value, which is that r value up to there. Good. Just r. That's what they're working with, or that's what the author is pointing out here, that this can be just thought of as r that goes out to the center of our cylindrical shell. Okay, so if we let delta r equal to r sub 2 minus r sub 1, the thickness of the shell, right? Going back to this thing again, if I add them and divide by 2, I will get that. But if I think about the r sub 2 value minus the r sub 1 value, that's going to give me this thickness. That's going to give me the delta r, the thickness of my cylindrical shell. Good. So we're just developing a formula here. Remember, we did the volume of the outside minus the volume of the inside. We subtracted them, we factored, and then this guy can be thought of as the mean r value between the two. And now this is the delta r. Right? This is going to be the delta r value. And this is just the mean r value. Just r as we did it in our picture, which is sort of the mean of the two, the average of the two radiuses. Good, 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 good. Okay, then the formula for the cylindrical shell becomes 2 pi h delta r, and it can be remembered as the, wait, where is the, times the height times the thickness. Why is this? Stop it. What the heck? There's a typo. Like, what the heck's happening here? There's an R missing. The volume is equal to 2 pi times R times H times delta R. Okay? And that comes from here. So 2 pi R times H times delta R. Good. Questions, 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 questions. Which becomes the circumference times the height times the thickness. Think about this guy here. One thing we could do, right? So remember, we got our bun cake, we cut it from the top down, and we got this shell. Once we have this shell, think about cutting this shell open. from like say right here, and I cut it open. That was ugly. From there to there, and then I cut it there. And then I roll it out. If I cut it right there and roll it out, what I would get is this little rectangle that would look like this. It would kind of have this on its edge, like that. And then it would be this long piece like this. Is that okay? This thing here, if I slice it right there and roll it out, it would be kind of like a big rectangle like this. And the thickness of it would still be delta R. Right? That would be the thickness of it. And then the height of it would stay the same. That would be h. And then this distance right here would be the circumference. Except that we have two circumferences, because we have the circumference of the inside one and we have the circumference of the outside one. So it would be approximately the circumference of the mean of the two. So approximately equal to pi, 2 pi r, where r, remember, is the mean of the two. It's this r right there. Good, 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 good. So if we multiply the 3 together, we get the volume of this almost rectangular shape. Good. And that's what we end up with over here. So it sort of makes sense. We have 2 pi and then r, where r is the average of the two radiuses, times the height, times the delta r. Any questions? Good.
I have a quick question. In the segment that's created from the cut, that green square that you extrude to the edge of the circle, would there be some sort of round at the end of that, like a fillet, that we have to account for? Or just because it's an approximation, does that matter?
Exactly right. So there would always be a little bit of space there, right? Because our actual cake has this smooth, our actual cake has got like a smooth curvature there. And if I cut through it, see how right here, I intentionally made it like a weird shape thing here. So either it might be a little bit too big, right? Maybe my cylinder goes a little too high, or maybe it's a little bit too small, like if I cut it and I do this kind of thing. So that there would be this little gap here. So remember that if we're going to approximate this shape, this cake shape, with 10 of these cylindrical shells, it will always have little gaps that are a little bit too big or a little bit too small. What we want to do is let that go out to infinity. And if we let that go out to infinity, those spaces become infinitely small, and then at infinity, we get the exact volume. But if you ever stop anywhere before infinity, then you'll always just get an approximation that might be a little bit too big or a little bit too small.
Okay, thank you for clearing that up.
Sure. I think there might be some nice images in here somewhere. Do they see here? Oh, perfect. See how here the author created a nice little image where there's 1 shell, 2 shells, 3 shells, 4 shells. There's like 5 shells drawn in here. Remember that, just to be clear, each one of these shells looks like this. So it's not very thick at all. It doesn't go all the way across. When I first saw this, I remember thinking that this is a bunch of coins stacked a bunch on top of each other. And then I thought, no, they're like a bunch of washers stuck on top of each other. And that's not quite right, neither one of them. It's almost like an onion, where it's like very thin little shells of onion is what's happening here. So this one right here goes all the way down. The second cylindrical shell, for example, goes all the way down to the ground. All of these go all the way down to the ground. And the thickness is not very thick. But anyway, to get to your point, this approximation is not that good. There's a bunch of little gaps there everywhere, so it's not going to be a very good approximation. But now when we push it out to more, then we get an even better approximation. And if we keep going, ad infinity, this will give me a perfect answer. But before that, it'll always be off by a little bit. Good. Good. Okay, so back to this guy here. Okay, so we have our formula in general, sort of general space here. But now if we tie down our equation back down to the x and y axes, so here is some generic function f of x, not necessarily the one we were working with, but just any function f of x, and we're going to rotate it this way about the y-axis, so we end up with our cake-looking thing that looks like this. Remember, we're going to come down from the top down. Our knife comes from over here like this, so it's going to come down and puncture it there, and go all the way across, all the way around, and it's going to come all the way down to the bottom, and it's going to be a very, very thin shell that comes all the way across. Okay, so we're going to get all these little thin shells. But connecting it to the x-axis, then the radius is going to be exactly equal to x, right? The chosen value along the x-axis. So for any specific value of x, where we choose to do this little cut, we'll be able to get our radius. Now again, technically there is an outer one and an inner one, but as we let this go out to infinity, we want those thicknesses to get infinitely small. So we're just going to let it be some x value somewhere inside that little gap for any one of these choices, and it'll be approximately what we need. Okay, so we're going to divide the value from a to b into n intervals, so little intervals, right, n of them. And then inside each one of these, we're going to randomly pick one value. So we're going to randomly pick one value in there. And then that'll be our x sub I value, right? Each one of these things is going to have a width of delta x, right? Each one of these things is going to have a delta x. So that means that the width of this thing is going to be delta x, the width of my little shell. Good. And x sub I bar is going to be the midpoint of the ith interval. So the midpoint, we're going to let this be equal to the midpoint of the ith interval. And then that'll be a very good approximation for our radius that we need for our shell. Good. Good. Okay, so then this is going to be the volume of one single shell. Let me zoom into this guy over here. We're going to have x sub I minus 1, x sub I over here, and somewhere in the middle would be x sub I bar, which is right in the center. That'll be my radius. So if I think about the volume of that particular one, remember that if I slice it up and roll it out, it'll be one big, almost like a big rectangular prism. And I need a width. The width will be delta x. That's going to be this width. This delta x is the width of this guy. I'll put it over here. Delta x, right? Because it's this thing. It's delta x. Delta x is the difference between x sub I minus x sub I minus 1. And if I'm dividing my entire interval into n equal intervals, each interval is going to be a delta x. Okay. Next, I need the height. The height of this value, the h value, the height, is exactly equal to that point right there, which is f of x, evaluated at this point in the middle, which we said was x sub I bar. So f sub x sub I bar, plugging in the x sub I bar into the f function will give me the height. Right? This is the width. This is the height. And now we need the circumference all the way around to give me the volume of this. Good. Questions, 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 questions. So we have something that kind of looks like this. Rectangle kind of comes across like this. And that's where, if we sliced it here along the x-axis, then it would say maybe be this guy here. Here is the slice along the x-axis. So if I sliced it across the x-axis, then sort of in the center there would be x sub I bar, would be a point right there. And then this would be the x sub I minus 1. And this would be the x sub I value. Good. The height goes all the way up to, well, we're going to approximate it to be equal up to the center. So we're going to say that the height equals to f of x sub I bar. And then this distance here is the circumference. And we have an inner circumference based on the radius value that goes from the center out to x sub I minus 1, minus 1. And the outer radius that goes out from the center, the origin, all the way out to x sub I. But we're going to approximate it to just be about as much as this, x sub I bar. So this is the circumference of the circle, which is 2 pi x sub I bar. Good. And that's where this comes from. Any questions? Any questions? Any questions? So in this rectangular thing over here, this becomes sort of the length. That's this length over here. And then the width, the thickness is delta x. The thickness of this thing is the delta x. And the height is the f of x sub I bar. Any questions? No? No? No, 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 no? Okay, so then we come out with a formula. Here's a formula that describes the sum of n of these cylindrical shells. And then, of course, we're going to let the limit as n goes out to infinity, the limit as n goes out to infinity of this equation is going to give us my integral. My integral of 2 pi x f of x dx. Right? Remember that as n goes to infinity, those delta x's are going to get infinitely small. So saying x approximately equal to the mean of the mean value inside each delta x is approximately equal to x. And so this will be as x ranges from A, x goes to B, from A to B. Right? Looking at my picture over here, we're going to let it go from there to there. So in this little image, there will be a hole in the center. Any questions so far, kind of, maybe? Maybe. Okay, thus the following appears plausible. The volume of a solid in figure 3 obtained by rotating about the y-axis, the region under the curve f of x from A to B is equal to this. Right, so it's just repeating this. The volume of the shape is equal to this. Okay, so in general, there's a nice little graphic of kind of slicing it and rolling it out. The length here is equal to the circumference of this guy. That's 2 pi x. And then the delta x is the width of this guy. That's going to be the width there. And then the height is going to be the value of f of x. So this little formula here will tell us the formula we need for the cylindrical shells method to find the volume of something. Any questions, any questions, any questions? No? And this is from x ranging from a to b, so we have to be careful about where we're going. Remember that we only care about the positive end of the x-axis because we're rotating it. So we wouldn't want to go from x goes from -3 to +5 or something like that. We really only care about the positive sides, and it might be a little section, not necessarily starting at 0. Okay, so we probably have a pretty good idea, but you know, nothing beats actually seeing it. So let's say here's back to the original question we were looking at. Here is an equation that gives you this guy here, right? So this curvature, this guy right here is the curvature y equals to 2x squared minus x cubed. Good. So for any value of x, we have one unique value of y, right? So the relationship between x and y is given by this guy. So one individual shell, we know that this is going to be the height. This is the height, right? This guy. Good. The delta x, well, that's just the thickness of the shell. That's easy. And then the radius is going to go right there. It's just going to be x. And x is going to range from 0, and we're going to want to do this all the way out until we get to here. The x goes to 2. Okay? So the volume is going to be equal to the integral as x goes from 0 to x goes to 2 of the shells. And each shell is going to be made up of a circumference times a height times a width. And that width is going to be delta x in this case. Also circumference, which I also called at the length, the height, and the width. Right? Again, that's if I take this guy and roll it out. I took that shell, this shell right here, and I would get a little something that looks like that, and then roll it out, and I would get something that looks like this. Only less ugly, but you get the point. So the width of it is going to be that delta x, which were also dx. Okay? Delta x, dx, same thing. And then the length of it is that circumference, right? Which is going to be the circumference. It's the length if I roll it out. If I don't roll it out, then we're talking about the circumference. Good. And then the height stays the same. And the height is going to be that guy. Okay, so we're ready to set it up, right? So the volume is going to be the integral as x goes from 0, x goes to 2 of 2 pi x, that's the circumference, times the height, that's the 2x squared, oh, come on, 2x squared minus x cubed, that's the height, times the width, which is dx. Good. Okay, so setting it up is the hardest part. Now all we have to do is solve this guy. Not bad. It's going to end up being a pretty little polynomial. This is a constant. We can pull it out. So my volume is equal to 2 pi integral of, and I'm going to distribute this x, so I'll end up with 2x cubed minus 2x cubed minus x to the 4th power dx. Again, x is ranging from 0 to 2. That's a nice, pretty polynomial. So the volume is equal to 2 pi, and then that'll be 2 times 1/4 x to the 4th power minus 1/5 x to the 5th power, evaluated as x goes from 0, x goes out to 2. That simplifies to a half. Bam, bam, that gives me a half. So this will end up being, I'll put it over here. This will mean that the volume is equal to 2 pi, and then 1/2 x to the 4th minus 1/5 x to the 5th, evaluated from 0 to 2. So the volume equals to 2 pi, bracket, and it'll be 1/2 something to the 4th minus 1/5 something to the 5th minus, luckily this is going to be a 0, so I really shouldn't even bother with it, but just to make sure people are still following where we're at. Get this, and now we put a bunch of 2's here, a 2 there, and then a 0 there, and a 0 there. Luckily all of this is just going to be 0, minus 0 goes away, and over here I'll end up with volume equals 2 pi times, this will be 1/2 times 2 to the 4th power is 8, that should be in parentheses, minus 1/5 times 2 to the 5th power, 2 to the 4th power is 16. I'm already dividing it. 16. And then 1/5 times, and then this will be 2 to the 5th power is 32. Okay, let's leave it alone and do common denominators. So that means it'll be times 5 here, times 5 over 5, times 2 over 2. And I'll get that this, I'll get that this is 2 pi. This will be 80 minus 64 over 10. So that's 16 over 10. 2 pi 16 over 10, which is 16 over 5. So that would be 16 pi over 5. I hope that's right. Well, let's see what the author got. (16 pi over 5), same thing. And circumference and height, yep, looks good. Any questions then about what I did anywhere?
Hello, Professor.
Yeah.
I always kind of get stuck in, I guess, the antiderivative.
Yeah.
When you get from the, where you got to the 1/2 x to the 4th. Can you explain?
This right here?
Just briefly explain that again. From to it, yeah.
From here to here? Okay, so the antiderivative of a polynomial, well, we have to really think about derivatives. So remember that if we had, let's go here. Whenever you have a polynomial, so the derivative with respect to x of any polynomial that looks like this, say x to the second power plus 3, oops, about 3x minus, I don't know, 1/4 x to the third power. Okay, when we're taking derivatives, remember the rule was to move this exponent out in front, like a linear factor, and subtract 1. So as we find this derivative, we get a 2x to the first power, right? We put it out in front, subtract 1, plus 3 times, and then we move this out in front and subtract 1. Oh, get x to the 0 power. So get that. Minus 1/4 times 3. You know what? I should have inserted that 1 in here. Times 1 times this. Okay, and then x to the second power. Now, x to the 0 power is just 1, so the whole thing can simplify. We often just kind of skip this middle step and go from here and just kind of jump to 2x plus 3 minus 3/4 x squared. Good, that's taking the derivative. Now, when we want to go backwards, we kind of have to think about this process, but sort of undo the process. So if I'm given this, and I want to think about what function exists out there so that I get an x to the first power when I take its derivative. So I have to think about adding a power. So it's got to be something to do with an x to the power of 2. And when there is a constant, I have to think about adding a power there, so I have to go backwards and think about this way. So when you find an antiderivative, often you just kind of have to guess and check and think about which function will do it. So going back to here, I have to think about what function out there gives me a power of 3. Well, that has to be a power of 4, right? Because when I take the derivative of this guy, the derivative with respect to x of x to the fourth power, that's going to be 4x to the third power. So I get the power that I want, except I didn't want that 4. I just wanted the x to the third power. The 2, I just left it alone. So my style is just to leave the constant and put it there, and then come up with something that gives me that. And so my first guess might be x to the fourth power, but that gives me this, and I don't want that 4. That's an easy fix. Come back over here and say 1/4 x to the fourth. Because now, when I take the derivative of this guy, come on computer, almost done. Now, when I take the derivative of this guy, then I do 1/4 times 4x to the third power, and now the 4's cancel, giving me exactly what I wanted. Good. So that's why I have a 1/4 x to the 4th. This by itself would give me just the x cubed, and I brought that constant out in front. So now I can simplify it and say, okay, well, it's actually 1/2 x to the fourth power. Good.
Oh yeah, thank you. That actually helps a lot.
Good, good, good. Okay, same thing with this guy then, x to the fourth power. I gotta think, okay, well, it's gotta be a 5, a power of 5, and then I just adjust for it. That's the way I think about polynomials. Now, if it's not a polynomial situation, then it gets more complicated, and you have to think about, you know, the complicated derivatives that we've dealt with, and then those lead to some standard antiderivatives that we just know. So if you just know the derivative of sine is cosine, then we're trying to integrate cosine. We know that sine is the function such that its derivative gives you cosine. So we always have to think about that. Find a function whose derivative gives you the function we're trying to find the antiderivative for. Okay, so let's go put it over here. This is what the author did. Same thing, only neater and prettier. That's why he gets paid the big bucks. Any questions then on any of this? Good, 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 good. All right, so this is a good place to stop for now. I'll let you practice some of these guys on your own, and then I'll try and do a couple more and kind of post them together. So look out for new videos soon this weekend. Okay. Any other questions on anything? No. So we'll meet again on Tuesday, and I will still be open to doing questions from either 6.2 or 6.3. So make sure you spend some time on it this weekend and highlight any questions you might have, and bring your questions to our meeting on Tuesday, and hopefully we'll get them answered. Okay. All right. Well,
Have a good day.
yeah, you too. Have a great day.